Okay, everyone. In the previous class, we started talking about some of the basic concepts that you'll need to know in order to understand the material that's going to come later in the semester. We talked about the effect of heat on atoms, makes atoms vibrate more quickly. We talked about the effect of pressure on atoms. It forces them to pack more closely together. We talked about the difference between gravity and magnetism. Gravity is the force of attraction between things that have mass, and magnetism is the force of attraction between things that have a charge. The bigger the charge, the bigger the magnetism. The bigger the mass in question, the bigger the gravity. And for both gravity and magnetism, the farther the charges, in the case of magnetism, or mass, in the case of gravity, are away from one another, the smaller those effects will be. We also talked about buoyancy. Less dense materials rise to the top of a system, and that works for gases. Less dense gas rises. It works for liquids. Less dense liquids rise to the top, like oil over water. And it also works for rocks. Continental rocks tend to be less dense than oceanic rocks, so when they collide at plate boundaries, the denser ocean plates tend to slip beneath the less dense continental plates. What I'd like to do with the rest of the class today is kind of continue on with some of these basic background concepts. And now we're going to talk about the Earth itself. We talked about the Earth's interior at the end of last class. It has an inner core that's solid nickel and iron. It has an outer core that's liquid metal and iron. So both of those zones deep within the Earth are extremely dense and too dense to rise through the next layer out, which is called the mantle. Again, we've never been to the mantle, but we have pieces of it that are brought to the surface through volcanoes, and we have lots of indirect evidence from things like earthquakes and some other methods that we'll talk about later this semester. Now what I'd like to do is talk about some of the Earth zones that you might be a little more familiar with, since these are considered to be the Earth's exterior, anything on the Earth's surface or above it. The hydrosphere is one of the things that really makes Earth unique. About 70% of the Earth's surface is covered by water, most of these in saline or saltwater oceans. The hydrosphere is obviously important because all of our life on Earth is water-based. Water is essential for just about every life form that we have. From a geologic standpoint, it's important because it erodes the surface of the Earth and modifies it over time. The other thing, too, that we'll talk about is that the hydrosphere is really important for humans and for other life forms because it buffers temperatures in the atmosphere. And what I mean by buffers is that it keeps temperatures within a fairly narrow range that life can tolerate. And one thing that water vapor does in our atmosphere is it moderates these temperatures. It keeps them within a narrow band. If we didn't have water on Earth, we wouldn't have water vapor in the atmosphere, and the temperatures would go through a much bigger temperature switch every day than they previously do. I'll try to give you an example of this. And it's all based on the fact that water is unique because it requires a lot of heat to raise the temperature of water vapor. Water vapor tends to hold on to a lot of heat. Different substances in nature hold heat differently. Think about what you use to cook with on your stovetop. You take a pan out, right? What is that pan typically made of? Usually some sort of metal. Aluminum, maybe copper. We don't make pans out of rocks, do we? No. Why don't we make pans out of rocks? Well, if you know much about how rocks respond to heat, you'll know that it takes a tremendous amount of heat to get the temperature of rock to rise. And then once it gets hot, it stays hot for an extremely long period of time. Well, that actually makes for really lousy cookware, because if you wanted to cook an egg in a rock pan, you'd be waiting an hour for it to warm up fast enough. so that you could actually cook your eggs. So that's why we use things like metals. Metals don't require as much heat to change their temperature. So they heat up fast and then they cool off fast as well. If you want to think about water in the atmosphere, think of it like that rock pan. It behaves really the same way. Water, like rock, requires a lot of heat in order for the temperature to go up. So it takes a lot of heat for the temperature to rise, but then it also takes a lot of time for that heat to dissipate and for the temperature to drop. That property that water has, that rocks have, something called heat capacity. Think about this. How many of you have ever been to Florida? Think about Florida in the summer. What's it like? I used to live in Florida, actually. I lived in Clearwater, Florida when I was in college during the summers. And when I would wake up in the morning, it would be about 86, 87 degrees, right at 6 in the morning. And the temperature would rise really slowly throughout the day. By mid-afternoon, it might be into the mid-90s. So it'd go from maybe 86 to 96. And then as the sun set, it would start to cool off. And by morning, it'd be back to 86. So every day in the summer, wake up, it's 86. Heat of the day, it's 96. Next morning, it's 86. Maybe a 10-degree temperature swing. Well, compare that to something like Arizona. Arizona is at basically the same latitude. It gets about the same sunlight. The difference is that it's in a much drier environment. It's not as humid. And if you think about summers in Arizona, I also lived there for a number of years. I remember waking up and it might be 50 degrees. Sometimes it's colder than that in the summer, sometimes a little warm. But an average day, let's say in Phoenix, Arizona, the mornings might be in the 50s. By mid-afternoon, it could be 110, 115 degrees, a 60-degree temperature swing as compared to what's going on in Florida where they might get a 10-degree temperature swing. The only difference between those two environments is the humidity. All of that water vapor that you have in the Florida environment is able to hold on to heat. It takes a lot of heat to get that water vapor to warm up, and then at night it takes a long time for that water vapor to release its heat and cool down. In Arizona, you don't have that kind of humidity, so the air is able to warm up much more rapidly and cool off much more rapidly. So as air cools, in order for it to cool, it has to release that heat to the environment. If you have a lot of water vapor, then you have a lot of heat to get rid of. So it takes a while. It just takes longer for all of that heat stored in that humidity to dissipate into the environment. So the temperature drop in here in humid areas is pretty slow. If you go to the deserts, or even here in Colorado in the summer, it's pretty fast. And as I said before, we have these two examples with Arizona and Florida in the summer. Florida is humid. The water vapor in the atmosphere is high. You'll be in the 90s during the day, 80s at night. All of that water vapor takes a long time to heat up, and then at night it takes a long time to cool down. Compare that to Arizona, where it's dry, low humidity, not much water in the atmosphere. You can get 110 degrees during the day and 60s at night. Much greater temperature swing. Temperatures are not well buffered because there's not enough water vapor in the atmosphere to slow down the rate of temperature change. So we'll come back to that concept. If you're having trouble with that, write your question down and ask me when I return in a couple of days. Okay, another little bit of background. The atmosphere. I just alluded to it in the last topic. We'll spend more on this later in the semester, but what I'd like you to remember for now is that the atmosphere is really pretty simple in terms of its chemistry. It's mostly nitrogen. Every breath you take in is about 80% nitrogen. You breathe in that nitrogen, your body doesn't do anything with it, your lungs don't do anything with it, and you breathe it right back out. The important gas for you as a living organism is the next most abundant element in the atmosphere, and that's oxygen. About 20% of every breath you take is oxygen, and that's one of the molecules that your body desired. It's necessary for your cells to function properly. You breathe it in, the hemoglobin in your blood picks up that oxygen and moves it to wherever your body needs it. So between nitrogen and oxygen, that's 99% of our atmosphere. There's another 1% out there. 1% might not sound like much, might not sound important, but it's, as it turns out, very important. That 1% contains things like CO2, methane, carbon monoxide, different carbon and sulfur gases, 20, 30, 40 different gases that affect how our atmosphere behaves can be found in that 1%. We measure them in really tiny amounts, but they have an enormous effect on the Earth's environment. And again, we'll come back to that a little later. For today, we'll just keep it simple. Atmosphere is 78% nitrogen, 21% oxygen, and 1% a lot of other things. Magnetosphere. Okay, this is kind of an interesting sphere that the Earth has. Some of you may have actually seen the magnetosphere before. If you've ever seen the Northern Lights, that is our magnetosphere actually going through some of its processes. As we talked about first day of class, the Earth behaves like a big magnet. Nobody's really sure what the origin of that magnetic field is. It's probably that outer core. Remember I said the outer core was liquid metal. So a liquid metal outer core has the ability to move around. And we talked about magnets being created whenever you have charged particles that are moving. Well, some of those metals in the liquid outer core have charges, and as they move around, they are probably responsible for creating our Earth's magnetic field. And the thing that's kind of interesting is if you think of the Earth as a magnet sitting out there in space, magnets attract and repel charged particles. And in space, there are actually a lot of different charged particles zooming around out there, emitted by different stars. And we have a star that's pretty close to the Earth. It's called our sun. And as it goes through its burning process, it gives off lots of charged particles that sort of whiz out in all directions in space. And they just go until they feel some sort of magnetic force out there. And many of them will just move through space and never really be affected by much. But the charged particles from the sun that come our direction are going to feel the Earth's magnetic field when they go by. And what happens is that our magnetic field attracts these particles, and they create kind of a protective shell that surrounds the Earth, and that's called the magnetosphere. The magnetosphere is pretty big. It actually extends out past the moon. Humans have never been without the magnetosphere for any significant length of time. Even the astronauts that went to the moon were protected by the magnetosphere of the Earth. So what this magnetosphere does, remember it's all these charged particles given out by the sun that are sort of held in place by the Earth's magnetic field. They create a shield that keeps out a lot of harmful radiation from space. Out in space, there are some nasty types of radiation. We have X-rays and gamma rays and various types of radiation that can really adversely affect humans. But we are mostly protected from a lot of that by this magnetosphere. So this diagram I just put up, so over to the left here would be the sun, where it says solar wind. That is all those charged particles that are being emitted by the sun. And they go out in all directions, but when they move past the Earth and feel our Earth's magnetic field, they get attracted to that and they form almost like a little cocoon around the Earth. And all those particles then interact with harmful radiation that's in space and help to filter it out before it gets here. So life forms on Earth, which include humans, really need to be pretty thankful for this, or else we would be bombarded with much higher radiation than we already get. Again, most of this comes from the natural process that the sun goes through as it makes heat energy in kind of this big nuclear furnace it has going. And sometimes all those charged particles will interact with one another, especially around our poles where they tend to be concentrated the highest. And you can get some pretty amazing interactions in the form of the aurora borealis, the northern lights, or the aurora australis, which are the southern lights, which very few people have actually seen. So, but I'm guessing a lot of you have actually seen the northern lights before. That's really the only visible telltale sign from Earth that we have a magnetosphere. So why am I even talking about this magnetosphere? It's up there, it's protecting us. Yeah, that's all great. Well, it's kind of interesting, and I don't know who first discovered this, but it's really a pretty amazing discovery, is that geologists back about 100 years ago discovered that the Earth's magnetic field actually flip-flops from time to time. That doesn't mean that the Earth itself flips over. The Earth would just keep spinning as it does. But what it does mean is that our magnetic field reverses polarity. So the positive pole becomes negative and the negative pole becomes positive. That's not something you would really see if you were looking at the Earth. The Earth would just keep spinning as it's spinning, but the invisible magnetic field would switch its polarity. Well, if you think about now, if you take out a compass, which direction is it going to point? Well, it points north, and it has through your whole life, through my whole life. What you might not know is that lava flows from just about every volcano on Earth have little tiny magnetic minerals in the lava called magnetite, and when they come out on the Earth's surface, they feel the Earth's magnetic field as well. And these little magnetic minerals in the lava will sort of wiggle around and point north, just like a compass needle. And then once the lava freezes, once it cools, those magnetic minerals are kind of locked in place, pointing north. Well, somebody started looking at the magnetic direction of magnetic minerals in older volcanic rocks, and curiously, they found that some of them point north. And then even older ones pointed north, and then even other ones pointed south. So you have sort of this north-south, north-south, north-south flip-flopping of the Earth's magnetic field. So what they surmise from that is that every once in a while, the Earth's magnetic field flip-flops. And we don't have any idea at all what causes this. It just happens from time to time. In fact, geologically, it's really pretty frequent. There's been 24 of these reversals in the past 4 million years. And if you do the math on that, that means that there's been about one reversal every 150 to 200,000 years. So what question do you have at this point? I bet the question that would come to mind first is, how long has it been since the last one? Well, we are way overdue for one of these. In fact, it's been almost 750,000 years since the last one. Why should you care? Well, a couple of reasons why this might be important. When we look at magnets in a lab, we can switch their polarity pretty easily. We do this all the time. What happens when you switch the polarity of a magnet is that the magnetic field for a brief period of time drops to zero while these poles are reversing. Well, if you think about that from a protection standpoint, if the Earth loses its magnetic field for a little while, then it loses its magnetosphere, and it loses its ability to protect us from radiation in space. So you have no magnetic field, no protection, a lot of radiation, and the concern is that maybe that could do something to life forms. Maybe it could cause extinctions. Well, as it turns out, if you think about how long humans have been on the planet, we've been on the planet about 2 million years, and humans as a species have probably endured 2 or 3 of these. magnetic reversals during that time. And we're still here. So it's not likely that these would cause extinctions, might not even cause mutations. One thing that it would really do today, though, and that we know happens, is that without the magnetosphere, all of this radiation in space would come streaming towards the Earth, and we have lots of satellites that are up now that would be adversely affected. So the point is that this is something that we should probably pay attention to, especially given that in the last 30 years the strength of the field has dropped by 30%, and that the site of the magnetic North Pole has moved around a fair bit. Again, always in the north, but it's appearing to be fairly unstable. So this is something that we'll keep our eye on, and hopefully it won't affect us during our lifetime, but it's one of those things that could. Okay, so let's move ahead. One thing I try to do in this class, I know a lot of you aren't going to be geologists or environmental scientists in your future life. A lot of you come from the business world or social sciences or education. So I would like in this class to try to make what we're talking about here as relevant as I can for you. And one of those things is looking at the importance of earth science in your everyday lives. So I'll give you a couple examples of how earth science affects you. One example, and one of the best examples of how politics and economics and geology and history all kind of come together, was in the 1990 Gulf War. Now, I know a lot of you weren't alive at that time, but in your lifetime you've seen some of the after effects of this war. I'll give you a little background on what happened. So, as it turns out, this war was fought for a lot of reasons, but one of the reasons was actually geologic in nature, and it had to do with an oil field. So here's a map of part of the Middle East. The white area here is land, the gray area here is water, the Persian Gulf, and these dark blotches are oil fields. So what an oil field is, it's a rock layer either beneath the Earth's surface or beneath the bed of the ocean that contains enough oil so that you can extract it for profit. Now, the Middle East has lots of oil fields, and they're very profitable because, one, they're not very deep, so you don't have to spend a lot of money drilling to get the oil out. And the oil is also what they call very high grade, which means that you don't have to spend a lot of money processing it to turn it into usable goods like gasoline and diesel fuel. So it's extremely profitable. Now, one of the biggest and most profitable fields in all of the Middle East is this Rumaila oil field. You can see part of it here in the upper part of the diagram. About 95% of it lies beneath Iraq. Here's Iraq, Kuwait, Saudi Arabia, and Iran. So you can see that most of it's in Iraq, but just that little bitty end there sticks over under the land of Kuwait. Now, this is not all that uncommon to have oil fields cross international boundaries. And usually what happens is the two countries that share an oil field will go to the bargaining table and come to some agreement about how much each country can pump. And that's usually the way it goes. It didn't go that way in this case. Iraq refused to bargain with Kuwait over this. Basically, they said, look, 95% of this oil field lies beneath our land. Just leave it alone. And, you know, to compound things, you're not really a country anyway. Iraq really never saw Kuwait as a sovereign country. They always saw it as actually being part of Iraq. So they said, you know, you're not a real country anyway. You're actually part of us, and 95% of it's on our property. And you know what? Just leave it alone. We're not gonna bother coming to an agreement over this. Well, Kuwait obviously didn't like that answer. And you have to remember, too, that this was during the 1980s. And at that time, Iraq and Iran were at war. And one thing that was really common at that time is they would bomb each other's oil facilities so that neither country could make money and use that money to buy more weaponry. So Iran was bombing Iraq's rigs on the Rumaila field. So Iraq quit pumping so that they wouldn't lose any oil during these bombing raids. Well, Kuwait actually saw this as an opening. They said, Iraq can't pump it, but we're not at war with Iran, so if we pump it, it's going to upset the Iraqis and maybe force them to finally come to an agreement with us. So Kuwait figured it could force Iraq to the bargaining table by stepping up production, and they pumped billions of dollars out of this field over a 5-year period. Obviously, Iraq is going to be upset. I mean, that was kind of what Kuwait was trying to do, was make them upset enough so that they would come to the bargaining table. Well, as it turns out, Kuwait greatly miscalculated, and instead of coming to the bargaining table, Iraq just said, it'd just be a lot easier if we just invaded Kuwait and just took the land back and all the oil. And that's what happened in August of 1990. The United States got involved a few months later, and when they came into Kuwait and forced the Iraqis out, one thing the Iraqis did is they set all of Kuwaiti's Rumaila oil field pumps on fire and created a pretty big environmental mess. So this was just one of the consequences of some dispute over geology. One final example I'll give you today is volcanoes. Now, here in Colorado, we don't live by volcanoes. But that's not to say that volcanoes can't affect us. They do. One great example is Mount Tambora. This is a volcano in the island nation of Indonesia back in 1815. And it was a large eruption. It ejected 37 cubic kilometers of ash into the atmosphere. Now, I know none of you probably have a good sense for what 37 cubic kilometers of ash really is. But to compare it, Mount St. Helens was actually 1 cubic kilometer. So this eruption was about 40 times bigger. So here's Indonesia right here, island nation, over 1,000 volcanic islands. Many of those volcanoes are active. Tambora erupted right about there. There's a satellite image of it over on the right. That crater is about 8 miles across. It's a real beast of a volcano. I flew over it about 15 years ago. It was really impressive. When that erupted in 1815, obviously the effects nearby were pretty devastating. 92,000 people died through starvation. Now, if that happened today, you wouldn't see nearly this death toll because we have more advanced means of transportation. We'd be able to get food and supplies and medicine there and greatly reduce the loss of life, but it would have still taken a pretty heavy toll on the local residents. But the interesting thing about this volcano is that it affected the Earth worldwide. In Europe, they had massive crop failures. They basically had a year without a summer because they had multiple instances of freezing temperature, which wiped out all the crops. There was massive starvation worldwide, lots of livestock deaths. It even snowed in Central Africa. 1816, the summer afterwards, which was the coldest summer after the eruption, that's when Mary Shelley began writing Frankenstein, which some people attribute to the really horrid, gloomy weather they had in the year or two that came after this big eruption. Worldwide, on average, they had a 1 to 3 degree sea temperature drop. Now, it doesn't sound like much, and this is something we'll talk about when we discuss atmospheric phenomenon and global climate change. 1 to 3 degree temperature drop doesn't mean it's 1 to 3 degrees cooler every day. A lot of days it may be normal, but then maybe 1 or 2 days a month you might get a 20 degree cooler day, and that might be all it takes for crops to experience freezing temperatures. So this can be pretty devastating. And the reason I tell you this is that volcanic eruption, even though it's one of the biggest in recorded history for humans, it's actually kind of tiny geologically. Mount St. Helens was 1 cubic kilometer. Tambora was 37 times bigger. Yellowstone, a nearby volcano to here, was actually 2,500 times bigger than the Mount St. Helens eruption. Here's a little diagram to show. There's Mount St. Helens from 1980. There's Mount Tambora, one of the biggest in recorded history. And then here's Yellowstone from 600,000 years ago. It is enormous. That's a picture of Mount St. Helens. So he had an ash cloud here that threw ash up to 100,000 feet, and it did it for 18 hours straight. And that actually cooled temperatures off worldwide for about a year. And that entire big eruption cost over $1 billion in damage. It shows up as that tiny little blip compared to Mount Tambora, and then compared to Yellowstone, which was 2,500 times bigger than that. Why do I tell you this? Well, you've probably heard that Yellowstone is a potential candidate for a volcanic eruption, and it will certainly erupt at some point in time. When? That's the big question. What I can tell you is that Yellowstone's actually erupted multiple times. It erupted 2 million years ago. Great big eruption. It erupted 1.3 million years ago. Great big eruption. And it erupted 600,000 years ago. Again, big, huge eruption. Now, if you do the math, you'll see that Yellowstone erupts every 700,000 years or so. And it's been 600,000 years since the last eruption. So we're coming into this window where Yellowstone might be due for an eruption. Now, I wouldn't go sell your property in Wyoming, and geez, if I could move to Wyoming, I probably would do so. It's not likely this is going to happen in our lifetime. In fact, I can pretty much guarantee that it won't. But geologically, we are entering a time period where Yellowstone might start getting restless. And if a volcanic eruption of that magnitude ever did happen, you can imagine that the consequences would be pretty dire for humans. If you think about it just in terms of food, we have 7 billion people on this planet. We already have a shortage of food in some areas. Worldwide, we only have about a 45-day supply of grain. And with one summer where crops are being wiped out because of freezing temperature, the entire world could really suffer from a lack of food. So it's something that I wouldn't worry about too much, but there's always a potential that Yellowstone or one of the other large volcanoes on Earth could do something that could severely impact us. So these are just a couple of examples on how different geologic events either have affected you in the past or could affect you in the future. Okay, so that is it for the background. When we meet again next class, we're going to talk about population, what human population is doing, how it differs from region to region, and how it might impact the availability of resources. Now, in preparation for our next class together, and this will be my first class back from South Africa, I want you to think a little more about this topic of human population. Right now we're at 7 billion people. We're adding 1 billion people every decade or so. How long can we keep adding that much people without experiencing some pretty severe effects? Or are we already experiencing some severe effects? Or if we add 1 billion people, is the world going to be a better place for us? What exactly is 1 billion more people going to do in terms of how it affects your life? That is the unknown, and that's something I want you to think about. So I know you've heard about how humans are impacting the Earth, and you probably even at this point have your own opinions on whether a population of 7 billion going on 8 billion is good for the environment and for humans. I have 2 videos that I'd like you to watch that take very different views of what expanding human population will result in. One is kind of a doom and gloom look, and one is no. adding a billion people to the earth isn't going to be a bad thing. So I'd like you to watch both of these. And then after thinking about it a little bit, I'd really like you to write a one paragraph, just one paragraph, that's it, I don't want any more, that summarizes your view on whether you think growing human population is good or bad for the environment. So I'd like you to type out a paragraph, email it to me by Monday night, September 5th. That's the night before our first class back together. In your paragraph, you should refer to one or both of the videos, hopefully something you learned by watching them, that you can use it as an example to make your case. And just, again, send me a paragraph on, do you think growing human population is good for the environment, bad for the environment, indifferent towards the environment? Just tell me your view. There's no right or wrong answer to this. We will all find this out in the future. But I want you to look at these two very different views and think about it. So with that, this should keep you busy until I return, and we will pick up from there. Again, write down any questions you might have, and I can review and go back through some of these topics on our first class together on Tuesday. I guess that is it for now, and I will see you next class.